Current density J. The current flowing per unit area perpendicular to the cross section is called current density. For example, here it is a conductor whose cross section is shown here, a circular part. If we slash it, then this the front part which we see is called cross section, and consider this as area S or A, whichever you consider. Then J will be equal to I by S if I current is flowing through conductor. Now unit of J equals to I by A, because I by S, J equal to I by S, so I, unit of I is ampere, and unit of area is meter square. So unit of area is meter square, so ampere per meter square. Per meter square. If at point P current delta I passes normally through area delta S as shown in the figure, current density J at P will be given by J vector equal to limit delta I by delta S sigma S tends to 0 into n cap, or that is J vector equal to di by ds into n cap, where n cap is the unit vector perpendicular to the area. Here it is shown current is flowing in this direction, and this is the area, cross sectional area. We have taken elementary cross section ds vector. So current density at this part will be a limit delta S tends to 0 delta by delta S into n cap, and J vector equal to delta di by ds into n cap. That is direction of J vector is along the direction of ds vector. N cap is unit vector perpendicular to the area. If the cross sectional area is not normal to the current, the cross sectional area normal to the current will be ds perpendicular ds cos theta. Here it is shown. That is, the cross sectional area is like this. We have we are slashing the conductor like this. So we will the cross section will look like this. So it is not normal to the current. So we have to take the normal part of this area. Now ds vector will be in this direction, because area is always perpendicular to the area vector is always perpendicular to the plane. So it will be in this direction, and current density is in this direction. We have to take component of this area in this direction, or this area component of this whole area into in this direction, and this will be called, and this area will be called ds perpendicular, or it will be equal to ds cos theta. So J equals to di by ds perpendicular equals to di by ds cos theta, that is di equal to j ds cos theta, or di equal to j vector dot ds vector. So this is also a relation, or I equal to integration di integration of j vector dot ds vector. In terms of current density, current is the flux of current density, and we know that any vector, dot product of any vector with area is a flux of that vector. So here vector is j vector, so it will be called flux of current density. In terms of current density, current is the flow of flux of current density. Note, we have J equal to I by S. If current is constant, J proportional to 1 by S, that is, for a given current, lesser the area, greater will be the current density, and vice versa. For a given current, lesser the area, lesser the current, for a given current, lesser the area, greater will be the current density, and vice versa. That is, if for this is S1 and current I is flowing, so, and here J1 and here S2 and I is flowing, because I dot current does not depend upon the cross sectional area, but J depends. So J1, and here J1 value of current density is J1 and here it is J2. Now as J is proportional to 1 by S, so lesser area will give more current density. Here current density will be more than here, because I equal to constant, that is J1 S1 equal to J2 S2, but as S2 is less than S1, so J2 is greater than J1. That is, current is a scalar while current density is a vector quantity. It is an important point. Next, the wire of a fuse in an electric circuit melts when the current density increases to 600 ampere per centimeter square. What should be the diameter of the wire so that it may limit the current to 0.4 ampere? Here given J equal to 600 ampere per centimeter square, or 600 by 600 ampere by 10 to the power 4 meter square, or 6 into 10 to the power 6 ampere per meter square in SI unit. Now I equals to 0.4. We have to maintain the current, this value of current. So 0.4 into ampere. Here area will be pi r square pi into d square by 4, where d is the diameter. Hence d will be, from this formula, d equals to 4a by pi. Again j equal to I by a and a equal to I by j. So putting this value of a area, here a is area but here a is ampere, so don't be confused. And so under root 4a by pi, putting this value of I by j, so d equals to under root 4I by pi j of 4 into 0.4 by 3.14 into 6 into 10 to the power minus 6. 10 to the power minus 6 under root 0.085 into 10 to the minus 6, 0.29 10 to the power minus 3 meter, or 0.29 millimeter should be the diameter. So diameter of the wire should be of this range, of this value. The amount of charge passed in time t through a cross section of a wire is given by qt equals to a into t square plus b into t plus c. A. Write the dimensional formula for A, B and C. B. If the numerical value of A, B and C are 5, 3 and 1 respectively in SI unit, find the value of the current at t equal to 5 seconds. In this problem, current is a function of time, so we have to find the current and also dimension of ABC. Solution. Here Q equal to AT square plus BT plus C. Now from the principle of homogeneity, dimension formula of LHS should be dimension formula for each term in RHS. So hence dimension of Q equals to dimension of this value A into T square, or dimension of A equals to dimension of Q by T square, or dimension of A equals to IT by T square, or IT minus 1. And then again Q equal to dimension of Q equal to dimension of BT. So hence dimension of B, dimension of Q by T, or dimension of Q is I into T. So TT so dimension of I. Again dimension of Q equal to dimension of C, hence dimension of C equals to dimension of IT. That is the answer. Now second, as I equal to dq by dt, so differentiating that value, 2a into t plus b plus 0, or 2a into t plus b. Now the value at hence I equals to t equal to 5 second, 2 into 5, value of a is 5 into 5, t equal to 5, plus b, value of b 3, so 50 plus 3 equal to 53 ampere. Answer. An electron gun emits 2 into 10 to the power 16 electrons per second. What electric current does this correspond to? Because I equal to q by t, so Ne by t. Now n equal to 2 into 10 to the power 16, E equal to 1 by 6 into 10 to the power 19 coulomb, and t equal to 1 second. So hence I 2 into 10 to the power 16 into 1.6 into 10 to the power 19 equal to 3.2 into 10 to the power minus 3 ampere, or 3.2 milliampere. The electric current existing in a discharge tube is 2 microampere. How much charge is transferred across a cross section of the tube in 5 minutes? Here we have to find the value of Q. Solution: given I equal to 2 microampere, or 2 into 10 to the power minus 6 ampere, or t equal to 5 minutes 5 into 60 seconds. Now we know that I equal to q by t, so q equal to it, 2 into 10 to the power minus 6 ampere into 5 into 60 seconds, 6 into 10 to the power minus 4 coulomb. Answer. So Q, the value of Q is 6 into 10 to the power minus 4 coulomb. The current through a wire depends on time, as I equals to I naught plus alpha t, where I naught is 10 ampere and alpha equal to 4 ampere per second. Find the charge crossed through a section of the wire in 10 seconds. Here I equal to dq by dt, so dq equal to I dt, hence q equal to integration dq, integration of 0 to 10 I dt, or 0 to 10 I naught plus alpha, putting the value of I, I naught plus alpha t dt, or integrating it separately, 0 to 10 and I naught t dt plus 0 to 10 alpha t dt. I naught integration of dt is t, 0 to 10 and alpha into t square by 2, 0 to 10. This will give 10 I naught plus alpha by 2 into 10 square 100, or 10 into 10, because I naught, the value I naught is given, plus 4 by 2 alpha value given into 100, about 100 plus 200, 300 coulomb. Answer. Our next topic is Ohm's law. The current flowing through a conductor is directly proportional to the potential difference across the ends of the conductor, provided the physical condition like temperature, pressure, strain, etc. of the conductor remains unchanged. This is the Ohm's law, statement of Ohm's law. That is, I proportional to V, or V proportional to I, or V equals to Ri. Here it is shown, this is the conductor, and current in this conductor is I, and its A in its potential is V, and at B in its potential is VV, and this is represented by a circuit diagram as it. This point is A, this point is B, and resistance of whole conductor is shown by R, where R is a constant of proportionality and is called electric resistance or resistance of the conductor, and this proportionality constant R is the called resistance of this conductor. Now VI characteristics. The graph between voltage and current is called VI characteristics, and we know that from the formula R equals to V by R, or delta V by delta I in the changing form, or here it is shown two different conductor A and conductor B. Now for conductor A, theta 1, if we take, this is the theta 1, and conductor B theta 2, and in this graph if we take, then this value will be theta, and this is a difference in volume, that is V2 minus V1, and in a given time interval delta, in a given current difference. So delta V by delta I Now delta v by delta I is so the slope that is equal to tan theta equal to slope of the curve. Now here tan theta 2 is greater than tan theta 1, and this slope represents tan theta represent r, so rv, because theta tan theta 2 is greater than tan theta 1, so tan theta rv resistance of b will be greater than resistance of a. That is higher slope of vi curve means higher resistance. Again here current here in I versus V graph is drawn. Now here tan theta will be delta I by delta V equals to 1 by delta V by delta I or equals to 1 by R. That is reciprocal of resistance called conductance. That is reciprocal of resistance is called conductance represented by G. Now here tan theta 1 is smaller than tan theta 2, or tan theta 2 is greater than tan theta 1, hence Rv is less than Ra, but Gb is greater than Ga, because here tan theta represent conductance, not resistance, or opposite of resistance. So what will be this value? Its opposite will be this value. So Gb is greater than, in this case Gb is greater than Ga, so resistance will be opposite, Rb is less than Ra. Definition of resistance. The property of substance due to which it opposes the flow of current through it is called its resistance, and for given body it is the ratio of applied potential difference to the resulting current. That is R equals to V by E, where V is the applied potential difference and I is the current flowing through the body. It is a scalar quantity and its SI unit is R equal to V by E, volt by ampere, or V by A called ohm, volt by ampere is called ohm. So SI unit will be ohm and represented by this symbol. Dimension. Resistance, dimensional formula of resistance, dimensional formula of V by dimensional formula of I, and dimensional formula of V is equal to dimensional formula of W, and dimensional formula of I is equal to dimensional formula of Q and T. So we have dimensional formula ml t minus 2 and q a into t. Sorry, here dimensional from v is equal to w by q, and already I is present, so we have written w by q, and dimension of w, that is work, is ml t minus 2, and dimension of q is a into t, and dimension a. So we can write m into L2 t minus 3 a to the power minus 2. Next point is that is reciprocal of resistance is conductance and represented by G. So that is G equal to 1 by R or equals to I by V. That is current by voltage difference is called conductance, and its unit will be ampere by volt called mho, or inverse of ohm, or ohm minus is called mho, and dimension will be m minus 1 L minus 2 T3 a square. That is reverse dimension of this. That is, this will be minus, this will be minus, this will be plus, and this will be plus. So m minus 1 L minus 2 TQ a square.